As you may know, the LHCb detector had many changes. A lot of pieces have been changed, and we're really looking forward to see the performances of this new shiny detector and also all of the physics performances.
The priority for Alice in Run 3 is the study of the collision of heavy nuclei, the lead nuclei.
LHC experiments plan to collect more data during LHC Run 3 than they did in the first two runs combined.
Most physicists expect that there should be some new particles beyond the standard model.
Most stable beams.
If there is new physics out there, we'll find it.
This is a good question. Give me some.
The Big Bang, 13.8 billion years ago.
We, Cern, are trying to understand matter.
We built a world-class physics laboratory with the most powerful particle accelerators.
After Cern physicists had received several Nobel Prizes for their work,
we built a bigger machine, the LHC, with bigger detectors.
Alice,
Atlas,
CMS,
LHCb. And after billions of collisions, we finally found it.
the Higgs boson.
We are a driving force for technological innovation. The scale and demands of our accelerators, detectors, and computing infrastructure
Constantly push the boundaries of technology.
Together with our member states, associate member states, and partners across the globe.
We develop state-of-the-art technologies in different domains.
1223.
Technology that impacts and saves
Power
lives.
Group 1224.
When the World Wide Web was invented, we offered it to the world.
1.8 billion websites today run on the World Wide Web for almost 5 billion web users. The technologies and scientific advances behind high-energy physics, through developments in accelerators, detectors, and computing, have historically contributed to the field of medical and biomedical technologies.
They also extend to a vast range of areas
such as aerospace, Industry 4.0, cultural heritage.
We are supporting the companies that use Cern technology and know-how also through the network of business incubation centers,
Human capital,
education,
outreach,
and open science. We are a powerful model for international cooperation,
taken as an example by other intergovernmental organizations and endeavors,
including in the field of climate change. We work together for a common good and are a proven source of inspiration for future generations.
and a model for other international research projects. Did you know that €1 invested in Cern's research brings back 1.8 euros to society?
Fundamental research in particle physics not only pushes back the boundaries of our knowledge of the universe,
but also catalyzes innovative technology developments.
We have had and will continue to have an impact on all of our lives and on the world around us.
Understanding our universe means going further than outer space.
We are Cern, and we are going back to the origin of our universe.
Pushing science
and pushing technology.
Explore the future with us.
So now we are ready to inject in the LHC in beam 1 and in beam 2, 3 bunches, 3 nominal bunches, up to 10 to the 11 protons per bunch. These bunches will be set up for injection and getting ready for ramp. Now
that the machine is filled, we will start the energy in ramp. So we will increase the energy of the protons to 6.8 TeV. For this, we will arm all the equipment. So arm means that all their equipment will be ready to receive the timing, and then they will all go together during the ramp to bring the beam to 6.8 TeV.
And this phase of prepare ramp, will be setting up all the systems in the LHC, from the radio frequency cavities to the magnets, the collimators. All these systems will be getting ready, synchronized, to start a ramp period together in 1,200 seconds. This ramp period of 20 minutes will be increasing the energy of the beam gradually up to a record energy that have never been achieved before in any particle accelerator, up to 6.8 tera electron volts. So now that we have reached this energy of 6.8 tera electron volts per beam, we will undergo the latest adjustments on the beam parameters and this phase of flat top before we start the new phase called squeeze.
We will now try to reduce the size of the beam. It's very important to reduce the size because the bunches are made of a lot of emptiness, if you want. So the more big your beam is and the less collision rate you have. So what we want to do is to decrease the size of the beam and like that increase the collision rate. For this, we have a phase that is called squeeze, where we will change the setting of our quadrupoles. And the quadrupoles are the magnets that we use to change the size of the beam. And this size will be reduced to the minimum.
So now that the beam size at the interaction points in each one of these 4 experiments is as small as a few tens of microns as a human hair, now a very complicated process of aligning these 2 counteracting beams, so reducing the separation of the 2 beams, such as they will be encountering each other at the center of each experiment. It's a process like shooting 2 arrows from the left side and the right side in the 2 beams and being able to encounter really at the precision of few micrometers level. And at this moment, the collisions will start to appear in each experiment.
For this, we have special magnets that will deviate the trajectory close to the interaction point, the experiment, so that they will be brought in the middle of the experiment and collide.
This dynamic phase now will last about 2 minutes. And after it, we'll be starting a countdown with each one of the experiments to ensure that they are ready for data taking. And it's only at that moment, after their handshake, that we'll be declaring stable beams.
Once we have declared stable beam, it means that the experiment will switch on their detectors and finally take physics data for the first time at 6.8 TeV.
It's an exciting milestone for Cern to be able now to accelerate beams to this new record energy and start data taking with this high luminosity in the LHC for this next few years, in which we perhaps will be discovering new particles or be giving more hints on new fundamental physics. So we are very excited. It's going to be a journey in the unknown.
Welcome to the Cern Control Center, the beating heart of our unique accelerator complex, where very tiny particles are fed into a complex and unique system of machines, particle accelerators, linear and circular, and eventually feeding collisions into the Large Hadron Collider. We're here today in what we call the LHC islands, where controls of the machines are taken care of by a team of engineers right behind me who are preparing for today an impressive new milestones, what we call the beginning of run 3, the beginning of a new season of data taking at the unprecedented energy of 13.6 tera electron volt. Today, for the first time, the detectors around the LHC machine where the collisions happen will switch on for the first time and start recording the collision and taking new data, marking the beginning of a new season for particle physics into uncharted territory. This is a process that we are going to share with you today live. That doesn't happen in a second. It takes some time to get to the conditions that we call stable beams, to then declare that we are ready for colliding and the detectors can switch on. And the process has already started some time ago. And so today, and I can ask now one of the operators, maybe Matteo, can you tell us where we are now with the process of getting to stable beams and then colliding at the highest energy?
So we have now completed the injection process. We have 3 bunches circulating into the Lhc per beam. And we are preparing for the energy ramp, so we are preparing all the system for this process, and in a few minutes we should be able to launch it.
That's fantastic. It's better than expected. So the beams are already circulating in the machines, and they are starting to increase their energy to reach the 6.8 tera-electron volt per beam and then collide and get the final total energy. So we will be following this process live right now, hopefully get to the collisions in time, and you'll be able to ask your questions. You can follow this live in 4 languages, English, Italian, French, German, and Spanish, and send in your questions, which will be asked in an hour or so, hopefully after collisions, by a panel, a wonderful panel of experts, including our Director General, Fabiola Gianotti, Director for Accelerators, Mike Lamont, the representatives of the 4 large experiments, and also of the minor experiments around the LHC. So good luck, LHC. Keep following us, send in your questions, and see you in a moment.
Start collimators. Start power group 23. Tune feedback is off for at least 1 plane of beam 1. Tune feedback is off for at least 1 plane of beam 2.
This on. And welcome back in the Cern Control Center. We're here today. Commenting in English with me is a very important person in the beams department. You are the big boss here. I'm here with Rodri Jones from the beams department, and you're helping me to go through this complex process of getting the beams into stable conditions and then collide. Is that an easy thing to do?
Well, right now, yes. It's becoming easier. The difference is that what we're doing now is going to highest energy ever. I think this is what makes it a bit more complicated than it's been in the past.
Right now, I can see we are increasing gradually the energy. This is called the ramping stage. And how long does it take to get to from the injection energy of 450 giga-electron volt, that is the energy with which the beams enter the LHC, to this enormous new energy of 6.8 per beam?
It takes about 20 minutes altogether. We'll see how long exactly it'll take in a minute. But once we start the ramp, basically everything is automatic, and we go up. It's called a ramp because if we look at the magnet current, which is what we have on the screen, you will see that it looks a bit like a skateboard ramp. It goes up to the top, and then it levels out at the top once we reach this top energy. And this is why we call it the ramp. We're going up in energy, and what you see on the screen is in fact the current of the magnet as it goes up, and we'll reach in fact 11,500 amps in these superconducting magnets by the end, which is what allows us to actually make the beams go in a circle around the accelerator at this very high energy.
And I know that the beams of protons, when they enter the LHC, they're already close to the speed of light. So increasing the energy doesn't make them faster, right?
No. In fact, they already come in nearly at the speed of light, and they hardly go any faster in the LHC, but in fact they get heavier. So they acquire more energy, which means they get more mass.
And that's what the experiments want. They want the highest possible energy to recreate the initial conditions of the universe, 100 billionth of a second after the Big Bang, right?
Exactly, this is what they want.
So we are now back to the control room we were seeing before the injection. And this is Mike Lamont, Director for Accelerators, commenting on the importance of Run 3.
Really good to be getting back in business. Obviously delays from COVID, a lot of hard work by the teams during the long shutdown to get the machine ready. Really looking forward to a new chapter in this remarkable machine. So higher energies and higher intensity beams from the injectors, making for a lot more data for the experiments.
Near him is Joachim Nech, Director for Research and Computing. telling us how important run 3 is for the LHC.
Excited about the start of the run 3. We expect a lot of more luminosity. That means number of collisions, proton-proton collisions than in the past. Actually, run 3 should double the number of proton-proton collisions. With a bit of luck, perhaps even a bit more than just doubling. Now, what is this good for? We will be able to do more precise measurements than in the past. For instance, measurements of the Higgs bosons, its properties, its couplings to other particles. And that's not all. We will also be able to search for rare processes that we expect to happen, but we, at this point in time, do not have enough data to do that. So we hope to see some of these new processes that we have never observed before, and maybe we will also get some exciting new discoveries of rare processes here. Now, it was not only the accelerator which has been improved over the last 3 years, but also the detectors. There have been new components installed, more precise, and I think this will also contribute to the extended physics science reach of the experiment of the LHC.
And that was Joachim Nicht, Director for Research, telling us how important it is, this milestone for the LHC experiments. You're now seeing again the LHC controls with Daniele Mirarchi, who is the engineer in charge today, right? You have a shift system whereby people happen to be in charge. Even if it's a special day, you don't choose who is in charge.
In charge, they run the machine. The machines that feed into the LHC as well, and this is operating the machines 24 hours a day.
We see that the ramp has reached more than 1,500 GeV. How are particles accelerated in the LHC?
In fact, most of the LHC itself is just to get the beam's background to where we actually accelerate particles, and this is done in a very small region. In fact, so around 10 meters or so of the LHC is actually used for the acceleration. As the particles come in to what we call these radio frequency cavities, we have a wave in the cavity, and this allows the particle to actually surf on this wave, and we give it a little kick, and then it goes the whole way around the ring. And every time we give it this small little kick as it surfs, every time it comes to the cavity, and this is what raises the energy in the machine.
And as we said, this raises the energy, make the particle more energetic because they are already quite close to the speed of light and they cannot go faster. Now we are back to the controls and we see the ramp ongoing. You see the energy going to 1.8 trillion electron volts already. There is also 2 more parameters, the beam intensity with beam 1 and beam 2, because of course LHC is a collider, so it gets 2 beams in opposite direction from the SPS. They collide in parallel. They circulate in parallel in 2 separate beam pipes, which are made to encounter at the points where the detectors are.
Exactly. So we have at the moment we have 3 beams per beam. In fact, 3 what we call beam 1 and 3 bunches in beam 2.
2 TeV and
these are
rising.
colliding at the 4 experiments. In fact, 2 collisions taking place in each of the 4 experiments with these 3 different bunches. It depends, of course, where they are in the ring, how they collide together. But each of the experiments will receive basically 2 of these bunches colliding when we reach the collision process.
And we now surpassed the 2 tera electron volt.
Yep, we're over a third of the way. So,
fabulous. And what about the beam intensity?
So the beam intensity shows how many particles we have in each bunch, in each beam, in fact. So here we have around 240 billion particles, and this means that these protons are actually distributed in these 2 bunches. So we have about 120 billion per bunch, and this is the number of protons that we have in these 2 bunches. So you can imagine that when they will collide, they will be basically 100 billion protons passing through another 100 billion protons.
It's crazy.
And every time they come together, they will then actually, a few of these will actually collide together to give the energy, which is then the ball of energy that we have, which is then where we see all the new physics.
So the more intense the beam, more collisions and the more data for the experiments, right?
Exactly, the more chance we have of colliding.
And this intensity is also somehow unprecedented this beam intensity, or have you done that before in previous runs?
At the moment we're at about the same level as before, slightly under what we've managed to do in the past. But during this run 3, what we will do is gradually increase this intensity to intensities that we've not used before. So basically doubling the intensity over the run.
Fantastic. It's ongoing. And today there's more than one person in the LHC controls. Usually in shifts I've seen only one person doing that.
Yes, at the moment of course there are a lot of people in the control room looking after this, and it only really takes one engineer in charge to run the machine, with a lot of experts of course behind, making sure that all these systems are
on call, right, in night and day. We are now seeing the main component of the LHC machine. This is a superconducting dipole magnet. This is a marvel of technology. And what does it do to the beams?
This is what is essential. You curve the beams to allow it to go around the ring. So basically the magnetic field that it creates deviates the particle in a certain way. This is what allows it to go around and around with a very high field, magnetic field in there, which means a very, very high electrical current in what we have. Superconductors, all of this at nearly absolute zero, so at minus 271 degrees.
There is a special shifter now in the controls of the LHC. I see our Director General taking part in this process of running the beam to the beginning of run 3. Is she familiar with what you're doing?
Indeed. Well, Fabiola is very familiar with it. She's followed the LHC from the start. She used to be a spokesperson for the Atlas experiment, and is very, very much involved and knows everything, in fact, that's going on in the LHC.
So she could even replace a shifter if you needed extra manpower. No, I'm joking. She's very passionate for physics, and every aspect of the process enthuses her, and she of course understands all that is involved. We are now seeing some special facts and figures about the LHC. It's really a unique machine. It's not just the largest and most powerful particle collider. It's superconductive. It's the coldest place on the planet, also the hottest at the same time at collision point. But look at all these statistics.
Indeed, so this is what we're aiming for by basically the middle of this year in terms of where we want to get to. So this is going up to around 1,200 bunches, basically per 2,880 bunches per beam colliding. And this intensity, which is not much above what we have now, in fact, will be the intensity of each of these bunches. And then all of these collisions happening at the same time. So basically, we're going around this ring, bunches at 11,000 times a second.
3.5 TeV
and
and rising.
each of these bunches is colliding together. So today we only have 2 collisions. So basically, 2 collisions every 11,000. But in the end, we'll have 2,808 or so collisions happening every second.
And you have 3.5 years of run, so you have time to increase the number of collisions that are happening. I heard an automatic voice, your LHC announcer. What does it do, and when does it start talking?
This is very helpful for the shifters, of course. This is what keeps an eye on what's going on in the background. So every time a new step happens, the announcer will announce this to the control room. Sometimes it's regular operation, so it'll tell you where we are in terms of energy, for example, that everything is going up and around. And then, of course, in case of an issue, this is also very handy. It'll tell you that you've lost the beams, why we've lost the beams if there is an issue, or if there is a problem coming up as well.
So we just said that we use dipoles to keep the proton that have the same sign, the same charge, two bunches of particles of the same charge kept in parallel along the same trajectory. Marvel of technology. Then there is another marvel of technology we are seeing right now that is part of the core of the machine, which is the quadruple. We have around 400 quadruples in the LHC. What do they do?
Standard quadruples are there for focusing modules, so you can imagine that these bunches
40 EV and rising.
remain in the LHC when we're running nominally for around 10 hours. Now this means it's equivalent to actually going to Pluto and back in terms of distance, and this means they have to be very well controlled, and anything which is slightly off trajectory will get lost on the way. So these quadruples are used to maintain basically the trajectories of the beam, so that we don't lose the particles on the way. These are very important. They're combined with the dipoles bend the beam, the quadruples focus the beam. Making the beams focusing along the way, we manage to keep them on this trajectory. basically go the whole distance to Pluto and back and remain collimated.
We're now hearing from one of the engineers in charge, Matteo Camillocci. He's going to tell us where we are. We can see where we are with the energy. So we are over 4 teraelectronvolts.
Over 2/3 of the way there, yes. And
that's great.
At the moment, it looks as though it's going as it should.
So Matteo is getting ready to tell the world what's happening.
We are now in the middle of the process of the energy ramp. So in about something like less than 10 minutes, we will be at the maximum energy. It was 6.8 TeV per beam, and then we will start the squeeze process. Okay,
amazing. Everything is going perfectly. That's really fantastic.
4.5 TeV and rising.
The announcer just said where we are with the energy. And rising, that's fantastic. It's encouraging. There should be a lady's voice next time you program the announcer. Just change the voice. And this is LHC page 1. I guess a lot of people are watching this page right now.
Yeah, so what you can see here is exactly what we said. This is the ramp. So this is what looks like this skateboarding ramp taking off. So this is basically the current in the magnets, and this is equivalent to the energy. So in fact, the scale you see at the right is the energy. And then the red and blue lines are basically the intensity of the beams. So we have a red, you see it on the screen as well, and blue beam. So we beam 1 and beam 2. So beam 1 the blue beam, beam 2 the red beam. And these traces show us how much beam we have in the machine. And if we lose any beam for any reason, this also then shows up on the screen.
And we should not forget that this is a big milestone, especially for the LHC experiments. And in their control rooms, we have as many people as we can see here today. And we are going around the ring, starting with interaction point number 1, where the Atlas detector, the largest of the 4 detectors, is located. Are we ready to talk to Atlas?
Hello.
Yes, I think we are. We are seeing an animation right now of where the Atlas detector is located. There are 4 interaction points around the LHC. Atlas is at point 1, and this is an animation taken from the real engineering design of the detector. Is super detailed. This is an enormous, the largest detector ever built on the planet. And we are soon going to talk to the Atlas Control Center, where we have Sarah Demers, I think. Is it?
Yes.
Hi,
hello.
Sarah.
That's
You're
right.
the data preparation coordinator. This is a big day for you. First of all, happy Higgs boson anniversary.
Thank you very much, and to you.
It was just yesterday. And so this is a super important milestone. You're switching Atlas again for the 3rd time for a new physics season. And it's more or less like the first time, isn't it?
Like the first time, this feels like nothing I've ever experienced before, actually. But yes, the room is really full of energy. People are excited. I think there's a little bit of nerves, but we feel ready for data, ready for run 3.
Thank you, Sarah. We'll come back to you when collisions are done. And good luck with this run 3. We are now going to the LHC interaction point number 2, where the ALICE detector is located. You can see, again, a very beautiful animation of the detector. It's all its layers. These are complex machines full of components and subcomponents, all built by universities and labs from countries from the entire planet. And at the center, the 2 beams are brought to collision. I now see Federico Ronchetti from the ALICE Control Center. You are the run coordinator. This is very important for you because finally you start running your detector.
Hi, Paola. Yes, exactly. So ALICE is basically a new detector. We have new components, new trackers, new online systems, new trigger, and we are really looking forward to see these high-energy proton collisions, as we need these collisions for our heavy ion program, and we also have a genuine physics program with proton physics.
So you're already happy starting with protons today?
Yes, extremely happy.
And we wish you good luck for the new season.
Thank you very much.
For the new run. And we come back to you when collisions have happened. And now we are continuing our run around the LHC ring, reaching point 5, where the CMS detector is located. These detectors are all around 100 meters below ground. They are all constructed in layers of very sophisticated electronics. Each layer has the task of identifying a different particle emerging from the energy created by the collisions in the center of the detectors. And I am now with Anne Dabrowski, the Deputy Upgrade Coordinator of the CMS collaboration. Hello, Anne.
Hi. Hello, Paula. Hi.
Your control room also is as full of people as ours today in the CCC.
Yeah. The atmosphere is electric here in CMS.
Are you ready for another Higgs boson discovery?
CMS is ready, for sure.
Happy Higgs boson birthday, first of all. And yes, CMS is ready, which means you've worked in the last 3 years upgrading your detector, and now you're switching it on for the first time.
Everything is ready. The detector is ready. The hardware is ready. The software. All collaborators have worked incredibly hard during LS2.
So just a few moments of patience, and you can start your new seasons of data taking for CMS.
Thank you, Paula. Thank you.
We'll come back to you when collisions have happened, and good luck for now.
Thank you, Paula. Thank you very much. We're waiting.
Bye. And last but not least, we're going to point 8 at the interaction point number 8 around the LHC ring. Again, the LHCb detector is located also 100 meters below ground. B stands for beauty. This is a very unique and beautiful experiment. And we are now talking to the physics coordinator-elect, Yasmin Amisa. Hello, Yasmin.
Hello, Paula.
So, I just said that LHCb is a very beautiful and unique detector. And you are now ready to take collisions, and this is unprecedented for you. Can you tell us why?
Yes, absolutely. So LHCb, as you may know, during the long shutdown has been entirely redesigned. So we have a new tracking system, new PID. The way that the data is processed is entirely different, and we're really excited to get to see the first physics result that we're going to get with this Beyond New detector.
And hopefully elucidating some of the mysteries you've already spotted in round 2.
Absolutely. We have a lot on our to-do list, and we're very excited to handle this in the next few weeks and months.
So I wish you the best of luck, and
Thank
we'll
you
get
very
back
much.
to you when collisions start, hopefully seeing some of the very first events. So we've completed our tour of the 4 experiments. We'll get back to them when collisions are happening, hopefully in time for our live to be finished. And we shouldn't forget that there are around the LHC also smaller experiments. The 4 detectors are huge, but there are also some smaller experiments, and we have one spokesperson for all of them, just presenting these experiments to us. These are Phaser, Snd, Lhcf, Moodle Map, and Totem. Here is Jamie
So as well as the
Boyd.
large LHC experiments that we've just been told about, there's actually 5 small experiments in the LHC, which they don't have their own collision point in the machine, so they're situated around the large experiments, and they see the signals coming from the collisions from those large experiments. So just to list through these experiments, so the first one I'm going to talk about is called Totem. So this is situated close to the CMS experiment, so it's got detectors that are 200 meters either side of CMS, very close to the beam. And it can use these detectors to detect scattered protons and to measure what's called the total proton-proton cross-section, which is basically the proton interaction rate at the highest ever energy when we go into run 3 at 13.6 TeV. So the second small experiment that I wanted to mention is called Lhcf, and this is situated about 200 meters from the Atlas collision point. Lhcf is situated very much in the forward direction of the collision, so it can see the collision products that go outside the Atlas acceptance, and this provides very useful insight, very interesting insight for cosmic ray experiments. Then I want to mention the Moodle experiment, which is placed close to the Lhcb interaction point and is designed to search for exotic new particles that could exist, such as magnetic monopoles. So Moodle actually has an ongoing upgrade which will allow it to also search for what's called milli-charged particles, which are particles with extremely low electric charge, and that will be an interesting new thing that comes in for run 3. Finally, I wanted to talk about two completely new experiments that didn't exist before the shutdown. They've been installed in the last couple of years, called Phaser and Snd Lhc. So these have been designed to search for neutrinos that are produced in the proton collisions in the LHC for the first time. In fact, neutrinos have never been detected directly from a particle collider, so this is really an interesting step forward. And these two experiments can also search for light, weakly coupled new particles that could be motivated by dark matter. And so this will really open a new sort of region of physics studies that can be done at the LHC. So that's the 5 experiments. I also wanted to just mention that there's, of course, the teams working on these are super excited about the start of Run 3. But for 2 of the experiments, it's the first time that they will ever see collision data, so that's extremely exciting to see how the experiments perform with this data. And then also, of course, to use this data to do physics measurements and searches. The other experiments have also had large upgrades during the long shutdown, both to improve their physics capabilities, but also to deal with the effect of radiation, which sort of deteriorates the detector performance during Run 2. So all of the experiments have new components, and it's going to be really exciting to see how these perform with the new data, and especially at the highest energy ever. So that's what it was.
So we have now Matteo Solfaroli telling us where we are with the ramping.
Per beam, and we have started the squeeze process, during which we reduce the dimension of the beams at the collision points, thus increasing the probability of collisions. This process will last for about 6 minutes, and then we will be in the position of start the collision process. Okay, it's finished.
So, Rodri, we reached the energy we wanted.
We've reached the energy, yes, and we're at 6.8 TeV, so GeV.
Fabulous, fabulous.
So,
6.8 tera-electron volt, that's fabulous. And you started the next stage, which is the squeezing.
This is called the squeeze. So basically what we're doing now is actually reducing the size of the beam in the middle of these experiments that we just saw. And this means that when the beams reach the center of this experiment, they're very, very small. They're only a few microns wide. And we do this so that there is much more chance of them colliding together when they actually come in there.
They are as small as a human hair, even less
They're
than a human hair.
much smaller than a human hair, yes.
We are now going to see how do you do the squeeze with these collimators?
Well, the collimators are used to clean the beam, so what's very important in a superconducting machine is to make sure we don't lose any of the particles along the way. And this is why we use these beasts that are called collimators. So any particle that is not directly in line with where we want it to be is basically cleaned away by these surfaces that we see on the side, and we lose them all in this region where we want to lose them, which is basically this collimation region, rather than in the superconducting magnets around the rest of the ring.
Okay.
And for a machine like the LHC, this is very, very important, because if we lose too many of these particles, we will basically heat up the magnets, meaning that they become non-superconducting, and this means we lose the beams. So the collimation system is a system which is very, very important, and basically make sure that we keep only the beam that we really want, the beams that are going to collide, and anything which is off trajectory we lose in these regions.
Where are they located, these collimators around the ring?
They're located in 2 main regions around the ring. One which is to clean away everything which is basically not at the right energy, and the other one to clean away the particles that are basically deviating in the trajectory.
Now we can see how collimated the beam is, that it becomes as small as the size of Spain on a euro coin.
Indeed.
It's really very much thinner than a human hair, almost invisible to the naked eye.
Yes, and this, of course, very important before we get into this squeeze process is basically to make sure that these beams are very clean. So basically these collimators are moved in along the ramp, and they follow the size of the beam. And then once we reach the squeeze process, basically here now we have these very strong quadrupoles that we saw earlier either side of the experiment, which are increasing in their energy and squeezing the beams down in the middle of these experiments.
So we are now going to take a look at the Cern data center, or the computing center, where we are going to talk to people that are also eagerly waiting for data coming from the LHC collisions and the LHC detectors. And they've gotten ready in parallel with the experiments in the machine in the last 3 years for the flow of data that are arriving. And I now see Enrico Porcari, our department leader of the Information Technology Department, ready to talk to us from the Cern data center. Good afternoon, Enrica.
Absolutely. Good afternoon to you all, and welcome to the data center. And I'm speaking to you from our own control center here at the data center.
Yes. Can you tell us where are you exactly, and what are you getting where you are?
Well, the center, this data center, has been in operation since the 70s, and it's been a shining example of innovation and continuously implementing new technologies, new hardware, new software, and it now hosts 450,000 processor cores and 10,000 servers that run 24/7 to store and analyze data coming from the experiments.
That's amazing. I think there is nowhere else in the world such a concentration of processor cores and servers, and then you run 24/7, of course, because you're receiving data from the detectors 24/7.
Absolutely.
Yes. Are you ready for this flood of exabytes?
Absolutely. The data center never sleeps, and despite the trigger system that quickly tries to filter data coming from the detectors and the experiments, experiments still produce vast quantities of highly complex data. And so for run 3, we expect twice the amount of data that we received in run 1 and 2 combined. So our challenge for LS2 was to really get ready to store and analyze 600 petabytes of data here at the data center. And if you put it in perspective, Paola, this is equivalent to 20,000 years of 24/7 high-definition video recording.
That's mind-boggling. I don't know how you do that, but it's amazing, and this is a challenge for everyone. LHC is a machine of challenges, and there are challenges at all levels, including the theory, to imagine the physics is going to do. Thank you, Enrica. We are coming back to you soon. And
computing center is waiting for all the data, and we are really very close to be able to produce that data. We went through the ramp with the 3 bunches. We are on the flat top, and actually then on the flat top with the bunches pass next to each other, and we squeeze the beam to very small dimensions, and then the next step is to put them in collisions, and this is about to happen at any moment.
Is it right, Rodri, what I just heard?
For this.
Renda is continuing.
As the beam gets into collision, we will adjust, and then the experiments will start giving us the luminosity figures. This means that they will send us the amount of collisions they receive. So we're waiting for the flat top and the squeeze to complete and to put the beams in collision. So I just look around and see on the display if this is already happening or not. Now we're still in the squeeze. So the collisions will come very soon.
Is that right, Rodri?
So
collisions very soon?
Indeed. We're getting very close to the collision process.
Around the experiments, so that do the squeeze, that squeeze to small dimensions, and then there are a few other magnets which now we will decrease the magnetic field in, and that means that the beams will go into collisions. The operators then will have to adjust these beams manually to maximize, let's say, the number of collisions we have.
Is off for at least one plane of beam 1. Tune feedback is off for at least one plane of beam 2.
I'm amazed. It took less than half an hour to get this close to collisions, Rodri.
When all goes well, it all goes well, and yes, we're very close. So I see now that we have squeezed, in fact, the 2 experiments down to what we call their final state. And they're now ready basically to start adjusting the beams. What we call adjust mode is to actually make sure that they start to get to collide together.
Start feedback dynamic change.
So we are going now to see the historical records of the LHC since the initial start.
We brought our first beams to an energy of 1.3 TeV, which was higher than the previous record from Teratron, which was 1 TeV. Then 1 year later, we pushed to 3.5 TeV. This was 2010. 2 years later, in 2012, we reached 4 TeV, which was the highest we reached during the first operating period of the LHC. This was then interrupted by a first long shutdown where we consolidated some parts of the magnets. This allowed us in 2015 to reach 6.5 TeV, again a new world record. We operated there for 3 years until we reached our second long shutdown where we did a further consolidation of the safety system of the magnet, which allowed us today to actually make the next step of 6.8 TeV, bringing us very close to the design energy of the LHC, which is 7 TeV. Now this is of course an important day for us because the beams reached this new energy for the first time. But it's only the start of a very long commissioning period which would bring us to actually collide the two beams for the experiments and provide the highest energy collisions, which should happen about 6 to 8 weeks from now.
And that was Jörg Wenninger, Head of Operations at the LHC Controls, commenting on all the records of this fabulous machine since its very beginning until 2 months ago, when you reached for the first time the nominal energy that we are having today.
Indeed, it's been we've been setting this up now, so after a long shutdown period we've got everything ready. We've managed to get all these magnets to actually stay at this very high energy as well, which wasn't simple, and now we're really getting very close to actually putting them into collision for the first time.
To today's big milestone, let's remind it that we are reaching the conditions with stable beams at the high energy so that the detectors can safely switch on and start recording. Why does it take so long between reaching the energy record and then giving the collisions at that energy record to the experiments?
We have to be sure that we can manage the beams, and this is what's very important.
So we are now collapsing the separation bumps. In about 2 minutes the beam will collide in the detectors, and so we can go.
So 2 minutes to go, Matteo said.
2 minutes to go.
Amazing,
so they're collapsing what they
amazing.
call these separation bumps. So while we ramp, of course, we don't collide the beams together. We make sure they don't collide. But of course, when we want them to collide, we have to, what they do, collapse the bumps. So basically take away the bumps is what's keeping them apart. And this is then pushing the beams closer together until they really collide in the experiments.
We are faster than expected. This is just amazing. We are seeing now the 4 experiments control room in contact with Daniele Mirarchi.
And then now they're just waiting for the collisions to actually take place. And as soon as the beams collide, the experiment should start to see something happening.
They are warming up. Warming up their hands, ready for a final applause.
So now, yeah, we're just doing the final checks before putting everything into collision. Hopefully everything is lined up and we actually get them to collide where they should collide. So that's of course not trivial either. And this is also why we've had to set things up beforehand, before letting the experiments actually turn on their very expensive detectors to take the data.
Start feedback dynamic change. Start power group 23.
2 minutes to go, I heard from Daniele. So we are sharing with you this beginning of run 3 that is happening in minutes right now from the Cern Control Center, connected with the control centers of the experiments. I heard that they are now ready for a handshake. So the control center of the LHC, the machine side, is handshaking with the 4 experiments control rooms.
Exactly. When we get close to actually putting the beams into collision and the control room and the operator in charge is very happy with what's going on, then basically there is this handshake process. So basically we allow the experiments to actually start turning on their detectors, to actually start taking data. So we're happy with how the beams are going, and basically that we're ready for them to actually switch on these very expensive detectors to start taking the first data of run 3.
It's a precision game in a giant machine. That's what's amazing. What really puzzles me with what you're doing.
Exactly.
Here.
It's very non-trivial, in fact, to actually put these beams into collision. So these are very small beams. We said much smaller than a human hair, and of course going around at 11,000 times a second around this ring, and we have to align them.
A 27-kilometer ring.
A 27-kilometer ring, and have to align them really head-on to allow these collisions to take place in just these 4 different points in the
One of the comparisons we make in communication is like shooting 2 needles on both sides of the Atlantic Ocean and make them collide at the center.
Exactly.
That's
this is how precise this has to be.
A sense of size, how precise you have to be. What is this graph they are showing right now?
This, I think, are the losses that they see, or basically the luminosity, I think. So this, in the end, should show that collisions are taking place. So basically,
so that's
at
a
the
screen
moment,
to watch.
exactly, this is a bit of noise at the moment, and they're just making sure that they can actually see something happening when they put the beams into collision.
Oops, the losses are less and less.
Now, no, I think there what you see is something shooting up on the right-hand side of the screen, which I think indicates that we are now starting to actually collide in some of the experiments. This will be confirmed later on when... So now I think we have confirmation that there is collision taking place, which means that we can then handshake with the experiments.
So we are in collision mode with the machine, but detectors are not switched on yet. We are waiting for the handshake.
Exactly. We're waiting for the engineer in charge to actually tell the experiments that they are allowed to switch on their detectors.
Start power group 1570.
So just some final adjustments being made to make sure that everything is ready.
Such a delicate process. The experiments are eager. I can see the faces of the people in the experiments control room waiting for this handshake.
And the announcer just telling the operators which power supplies it's adjusting to try and make sure that these beams are actually colliding.
Because you control one by one each power supply.
There are specific power supplies that are controlled individually to try and make sure that these fine adjustments are made, yes. Yeah.
Fabulous.
Start power group 1579. Start power group 1500.
So I think now what we see is that there is activity in each of the actual experiments. We see the 4 different graphs where we're trying to now optimize the luminosity, so basically how the beams are colliding, and we're just scanning the beams across each other to try and make sure that we've really got them aligned as they should be before we give the go-ahead to the experiments to actually start taking their first data.
Start power group 1587. Start power group 1588.
So these are what we call luminosity scans. So a luminosity is a measure of how many collisions are taking place at any time. And of course you can imagine that when we bring the beams together, these very small beams, they're not perfectly aligned head-on. And this means that we have to slowly move them left, right, and up and down to try and optimize where the collision point actually is. And this is what's going on.
This is the job of Daniele, who is now on screen.
Exactly. This is what's going on at the moment. These automatic scans that have been launched to try and make sure that we're now optimized before we give the
more
go
experienced
ahead.
Colleagues around him, because I think it's his first year LHC
it's
operator.
It's his first year of LHC operation, yes. He came on the team as we were in shutdown mode, so this is really the first year that he's been operating the machine, but doing a very good job of it.
Start power group 1599. Start power group.
So there we have, these are the different scans that are made. The dips are where we go out of collision, and every time it goes up, of course, it's where we basically optimize the collision points. So you can see that as we move away in the wrong direction, we actually go down in what we call luminosity, so how many collisions we have. And then as it's optimized, of course, we get to a higher and higher level, and this is what is now being done. And once he's happy with the level for each of the 4 experiments, he will then launch the handshake with them to allow them to start taking data.
It's a thrilling moment. Everybody is waiting. I think the experiments are already pleased that they are getting collisions, but they are not switching on yet.
Not yet. No. I think they want to really make sure that everything is fine before giving the final go-ahead for this.
Power group 1611.
So this is the final step that's not been done yet this year. So it's this move from this adjust phase.
It's a real
to
first
really the
that we
stable
are
beams.
sharing with the world today.
Exactly. So now
all the eyes are on Daniele
Daniele
Mirarchi, who has the luck or the bad luck of being on shift today, at the very moment where all the eyes of the world are on him. He's like an orchestra director setting the pace for the music to go.
But very calm, as you see. I think very professional, and knowing all the steps that has to be taken to make sure that this is all done in the right way.
This is a job that is learned on the job, right? There is no specific training outside this room?
Not really. There's a lot of knowledge, of course, behind, which has been acquired over the years in different ways for Daniela as well. But then the real on-the-job operation is learnt in the control room, of course.
Because you continuously adjust. We're ready to go.
Good to go,
ready
says
to
Daniela.
Go. Good to go. All languages are spoken in the control center. I hear Italian, of course.
Okay, so Atlas, okay for you?
I hope Atlas has heard. Atlas is thumbs up. Atlas is thumbs up. That is.
Okay.
That was.
Alice is ready for collisions.
CMS, are you okay?
Yes, confirmed here, ready for collisions.
LHCb, it's for you, okay?
Ready, go for it.
Yeah, fantastic.
So all experiments confirm that they're happy.
So we are counting down to the start of run 3, the moment when the experiments are going to switch on for the first time and be able to record collisions from the Large Hadron Collider at the center of their detectors at the record energy, unprecedented energy of 13.6 trillion electron volt. This is going to happen in 8 seconds from now.
6, 5, 4, 3, 2, 1.
Mode stable.
There we are.
And there we are. Run 3 has officially started. Fantastic. All the experiments are now recording their first collisions, and we have the Director General coming up to the floor to make a statement on behalf of our beautiful laboratory. We are starting the countdown again. What's happening?
We're in stable beams.
We are in stable beams?
We are in stable beams.
Are they
switched to
colliding?
stable beams. We're colliding.
We are colliding?
The experiments are starting to take
The experiments started to take the
run
data,
3.
but what happened to the Director General? She was supposed to come to make a declaration. Okay, so this is the arrival of the data from the collisions at the Cern data center, where they've installed an artistic installation. And these colors tell us that the data are actually flowing. This is
From
just
each of the experiments,
art.
yes, coming
yes,
in. Yeah.
And we will soon see the real data arriving to
So
the
this is
computing center.
Exactly. This is then
And,
transmitted from all of the experiments
Exactly,
into the
from the
computing
center of the detectors that we are seeing right now to the counting rooms of the detectors of the experiments, and then to the Cern data center, and from there to the world through the LHC computing grid.
Yes, and of course all the data, we can't handle this all at the same time, so at each of these stages we actually look at the data, see what's interesting or not, and only pass on the interesting data to the next level. And this is the way that we reduce the data and then make copies of it as well, and send this out to all these different places.
And this is happening right now.
And this is
right
happening
here,
right now.
right now. We're good for 3 more years of data taking at the LHC. And finally, we have the Director General, Fabiola Gianotti, ready for her statement on the beginning of Run 3.
It's a magic moment now, here at this moment in the Cern Control Center. We just had collisions at an unprecedented energy, 13.6 tera electron volt. And this opens a new era of exploration at CERN, a new chapter. Run 3 of the Large Hadron Collider will give us collisions at higher energy than before, and also an amount of data equivalent to the total amount of data recorded in the previous 2 runs. And this, of course, will increase our opportunities for discovery or for understanding the fundamental laws of the universe. C'est un moment magnifique au CERN. On est dans la salle de contrôle du CERN. On a juste eu maintenant des collisions à 13,6 téraélectronvolts, TeV. C'est une énergie sans précédent et c'est le début du run 3 du LHC qui ouvre un nouveau chapitre dans l'histoire du CERN, plus d'énergie, plus de collisions et donc plus de possibilités de découvrir de la nouvelle physique ou au moins de pouvoir affronter les questions ouvertes en physique fondamentale. Siamo nella sala di controllo del Cern, abbiamo appena visto collisioni a energie senza precedenti, 13,6 tera electron volt. È un nuovo capitolo che si apre nella storia del Cern, il terzo run, il terzo periodo di presa dati di Lhc e l'energia superiore dei fasci e l'intensità dei fasci, il numero di collisione, ci permetterà di affrontare le questioni aperte in fisica fondamentale con maggiori opportunità di rispondere.
And we are now going back to the control center. As we promised, we are going back to them after collisions. Collisions have happened. And we are now with the LHCb control room, where I see Chris Parks, the spokesperson of the experiment. Hi, Chris. Everybody is smiling. You were applauding before. This is a magic moment, as the Director General said, especially for your detector.
Really exciting time here. It's been 15 years in planning. We first started to design this new version of the experiment in 2007, and today we get to operate this detector with collisions for the first time.
This is wonderful, and we do hope that some of the hints that you've already seen in Run 2 are going to be clarified during Run 3 in the next 3 years.
Yeah, we really hope that we're going to collect something like 10 times as much data in this next run as we collected before. So hopefully we can see a whole range of new phenomena. Even today we announced the observation of 3 new particles that we observed from the data from the last runs. And let's see what we get from the next years.
Yes, we'll talk about the new tetra and pentaquarks later during the Q&A session. I'm sure there will be lots of questions for you guys, so stay there. Don't go away, celebrate, and we'll celebrate together later on. Thank you very much. Thank you, LHCb. We are now going to the interaction point 5. I see Luca Malgeri, spokesperson of CMS, ready for commenting the beginning of round 3 at the CMS. Hi, Luca, can you hear me well?
Yes, I can hear you, Paola. Can you hear me?
Yes, very well. Thank you. So, are you happy, CMS? Yes, I can hear everybody's happy. Round 3 has started. What's your comment, Luca?
Sorry, Paola, there was too much noise here. If you can repeat the question, please.
Yes, just a comment on run 3. What are you up to in the new run for the CMS detector?
Yeah, no, I mean, there was really 3 years of hard work for all the people that are here. Actually, there is a crowd here. We are celebrating. We have seen the first year, the first events there. It's really amazing, and it is really a celebration that we are doing here.
I hope you can show the events with us later on.
We are, actually, you can probably oversee the
we see the collisions in the middle of your detector.
Indeed, and this is what we were celebrating. So for us, it's really, I mean, these were really heavy 3 years, but we are really ready now to go for another. Yeah, we are asking for the main display. And I said that this will be fantastic because we are preparing our detector for the next years that come in run 3, really to go even past the doubling of the luminosity.
Fantastic.
In terms of reach.
So happy new exploration, CMS, and see you later for the Q&A, Luca.
Sure.
And it's now time to go back to Alice at point 2, where we see Luciano Musa, spokesperson of the experiment. Hello, Luciano. So celebrations at Alice as well.
Thank you very much, Paola. There is a great excitement here and also a growing fibrillation. You know, we've been preparing since several years, and now we're starting taking data with the fully revamped detector, which will allow us, so this is a very massive upgrade of the detector, the readout system and online computing system, which will allow us to study proton-proton collisions and a bit later in the year also lead collisions at much higher rates than it was possible in run 1 and 2.
That's fabulous. That's fabulous. Happy new season, Alice. And we'll see you later, Luca, for the Q&A. So we're now to Atlas. Fabulous. Andreas Hacker, spokesperson of the collaboration. I can feel the excitement. I don't need to ask you whether people are excited. We can see it with our own eyes.
Thank you, Paola.
hope you can hear me. You see, it is an absolutely overwhelming moment for all of us.
It's as if it was brand new detector.
Yes, indeed, and you can see also maybe on this side the beautiful collisions showing up here. Yes,
they're
exactly.
fabulous.
So, fantastic collision. So this is really an absolutely overwhelming moment for all of us. It is really beautiful to see highest energy beams ever. See cross and collide in Atlas and giving us physics data again. And I think for me, this is not the first time we restart data taking, but for many of the experts here, the young experts, this will be a lifetime experience for them. They're all now operating the new detector after this long upgrades.
Thank you very much for sharing this fantastic moment with everyone. We are now going to the data center once more. Enrica, are you being flooded with the new data from the LHC experiments?
Absolutely. The data is coming in fast and furious from the collisions in the LHC experiments and the detectors. And so all the data is coming in here in the room behind me that is hosting 450,000 processor cores and 10,000 servers that run all the time. As you could see from this animation, data from the experiments come into the data center, which is connected to the experiments via over 50,000 kilometers of optical fiber. That's more than the Earth's circumference. And so thanks to this network, we are now, again, receiving the first collision data. Now, when the data comes into the data center, two things happen to it. First, it's stored into disks, then it's stored into tape for long-term storage. And after another copy of it is provided to the worldwide Large Hadron Collider computer grid, with its 140 agencies that are connected to it in 42 countries, a huge collaborations to be able to provide to scientists worldwide the data that they need at their fingertip. So, and I think that's an incredible type of collaboration that puts together millions of computers that are allowed to provide more than 1.5 exabytes of storage capacity worldwide.
That's impressive.
So, yeah, that's absolutely an impressive collaboration achievement, if you ask me. And what you see in the screen here right now, that's the image of the data coming from the 4 experiments with the 4 different colors.
So this is live, Enrica?
This is absolutely live. And it comes so as the data is coming in, it's immediately pushed out to the WSCG collaboration centers, red for Alice, yellow for Atlas, orange for CMS, and green for LHCb. It goes to all the different in all the different centers, and I think it's the grid, as I said earlier, never sleeps. And it's thanks to the network upgrades that we've been able to do in the last 3 years that the speed that the data travels through worldwide is up to 33 gigabytes per second. That's a factor 8 higher than it had been during LHC Run 1. So I think we are ready for the data deluge that is coming in from the experiments, and so are all of our collaborating centers worldwide.
This is fabulous. This is better than a worldwide orchestra all playing together at the same time. And obviously, nobody ever sleeps at CERN. Everything is happening 24 hours on. Thank you very much, Enrica. You stay with us for the Q&A later.
Absolutely.
I'm sure there will be lots of questions for everybody at this special moment for CERN. Champagne.
So there we are, we're back in the control room, and we've got the champagne bottle ready for the world record highest energy collisions. Just waiting for this to be shared out with the team that's managed to put everything in place.
So we got the best of any possible scenarios. The feat was accomplished before 5.
In less than an hour.
Less than an hour, and you well deserve this bottle of champagne. We are now concluding the multi-language live. We continue in English with the Q&A session. Around the table we will have the Director General, the Accelerator Director, all the representatives from the LHC experiments, representative from knowledge transfer, and in remote, the spokesperson of the LHC experiments and the IT department leader. So I welcome everyone to continue sending questions to our dream team, the social media team, that will send them in to myself and will moderate. I will moderate this Q&A with the directors and the representatives of the experiment. So we're now going to see the highlights of the day. Before we start the Q&A, I take this time to thank very warmly and very dearly Rodri Jones, who helped me interpret what was happening and commenting and explaining. Thank you, Rodri.
Thanks, Paula. It's been a wonderful afternoon.
Thank you. Yes, we have questions from the social media. I also check here in case with the screen. Okay, that's it. So I'm going to share this microphone with you, Fabiola and Mike, two of you. You have one microphone on this side to be shared according to... Oh, sorry. It looked like one. There should be one on this side. Eva? Ah, okay.
This one.
Okay. Congrats, great life. We're so lucky. This morning we were not hearing you. You were a little stressed this morning.
Is this live or we have to do it?
It's nothing. Ciao, Giovanni. Thank you for being here. This is the VNR that is going to be given to the press together with images of today. And we were on a new It's a magic moment now here at this moment in the Cern Control Center. We just had collisions at an unprecedented energy, 13.6 tera electron volt, and this opens a new era of exploration at CERN. A new chapter, run 3 of the Large Hadron Collider, will give us collisions at higher energy than before, and also an amount of data equivalent to the total amount of data recorded in the previous 2 runs. And this, of course, will increase our opportunities for discovery or for understanding the fundamental laws of the universe. C'est un moment magnifique au CERN. On est dans la salle de contrôle du CERN. On a juste eu maintenant des collisions à 13,6 teraélectronvolts, TeV. C'est une énergie sans précédent et c'est le début du run 3 du LHC qui ouvre un nouveau chapitre dans l'histoire du CERN. Plus d'énergie, plus de collisions et donc plus de possibilités de découvrir de la nouvelle physique ou au moins de pouvoir affronter les questions ouvertes en physique fondamentale. Siamo nella sala di controllo del CERN, abbiamo appena visto collisioni a energie senza precedenti, 13,6 teraelectronvolt. È un nuovo capitolo che si apre nella storia del CERN, il terzo run, il terzo periodo di presa dati di LHC, e l'energia superiore dei fasci e l'intensità dei fasci, il numero di collisioni, ci permetterà di affrontare le questioni aperte in fisica fondamentale con maggiori opportunità di rispondere. And here we are, we're starting a Q&A session following a fabulous live. It's unbelievable, in less than an hour, we brought the beams to colliding for the first time, and the detector switched on. It's better than any wild dream that I could have. Fabiola, you commented right now, it's a new adventure that is starting for particle physics.
Yes, absolutely, it's a new chapter. Every new run is a new chapter. but this one in particular because there is an increase of energy and an increase in number of collisions, and more data, more energy means more, increased opportunities for measuring the Higgs boson, finding new physics, and in general addressing the open questions. And I would like to say that I've seen the start of 3 different runs, and every time is a big emotion. So also today there was a lot of excitement here in the control room.
Yes, and while the beams are colliding, this is a triumph also for the accelerator, for the Large Hadron Collider, right? We have here Mike Lamont, Director for Accelerators.
No, it's a great moment. It really is. The result of an awful lot of work by an awful lot of people to bring this together. I mean, this is kind of symbolic of all that effort, which will now go on over the next 3.5 years. The work continues, but here we keep colliding. We keep colliding, but no, it's fabulous to see it back in stable beams again.
So we have here around the table more people, because this is a collective effort. This represents exactly how CERN works. On the right-hand side of Mike Lamont, we have Patricia McBride, who represents the CMS experiment. We also have the possibility to talk, and they're following us from your control room to talk to the spokesperson. Hi, Patricia. Hi. Then we are talking, we have here Mateusz Ploskon from Poland, who represents the ALICE collaboration. And as well, in your case, the control room can be, we can talk to the control room at any time. Just to complete the tour of the LHC experiments, we have Manuela Winkter from the ATLAS experiment and the control room connected, and Niels Tuning from the LHCb experiment. We also have Jamie Boyd, who represents 5 new, less-known experiments, much smaller but not less important, that are around the LHC. Right, Jamie?
Yeah, that's right.
And we have Giovanni Anelli from the Knowledge Transfer Department, because, as we know, whatever we do at CERN, as Fabiola said, is unprecedented. And not only we go into new territory for particle physics, but also in technology. And new technologies emerge from our field that your department, Knowledge Transfer, makes sure get to the world. So we see now the control rooms of the 4 experiments, and we can start being flooded not just with data and collisions, but also with the questions. We also see the CERN data center ready to answer questions for our audience right here. So I normally should see questions on the screen coming up. Yes, please. Please.
As an experimentalist, I would like to congratulate the LHC accelerator people. Fantastic achievement, and we look forward to
Io porto l'SPS.
So I see a question from one of our social media. We have all of them streaming the live. Mimi Mariam is saying, this is for Mike, I guess. Is it true that the LHC will run for 4 years?
Yeah, indeed. We plan run 3 takes us through to the end of 2025, but we do stop for Christmas.
So you allow yourself a little pause for Christmas. And what's happening next?
What's happening next is, well, we're getting into business as usual. So at the moment, today, we had 3 bunches per beam. The target is around 2,500. So over the next few weeks, we're going to step up gradually the number of bunches per beam. When we get to the full complement, this is going to be the equivalent of a TGV going at 190 kilometers an hour, the energy in the beam. So we really have to be very careful as we do this staged increase in the intensity. So that's going to keep us busy for the next month or so.
Yeah. I now have a question for all of the LHC experiments. Now there is a question from Ronald Repice, the host of podcast, Dr. Ronan Filter. This is a nickname for... What are the practical applications of this collision? And Giovanni, yes. Maybe not just of the collision, but...
Yeah, indeed. So this is a great example of, how we work at CERN. To achieve the beautiful results of today, we push the limit of technology development. And all the technology that we develop at CERN can be used in other fields. So this is just one example of the physics that we do allows us to develop technologies which can be used in fields like medical. So we have concrete application of accelerator technologies in hadron therapy to cure cancer or production of radioisotopes. Then we have detector technology which can also be used in medicine, and there are many, many examples. So I would say there are plenty of practical applications which are which come from the fact that we constantly develop new technologies in the field of accelerator, detector, and computing, which can be used in other fields.
What I was asking is, yesterday we were celebrating 10 years of the Higgs boson discovery, especially for Atlas and CMS. Are you expecting to see more Higgs or anything similar to Higgs? Patricia?
We're expecting to see lots more Higgs and be able to do very precision measurements to understand what the Higgs is, what it's telling us about nature, and we're really looking forward to it for Run 3.
Manuela.
It's a really exciting time because 10 years ago the Higgs didn't really exist. We didn't know about it. And then we discovered it. And then we make precision measurements. And now we're actually using it as a tool to look for new physics. So it's become our workhorse now for what might be the next discoveries at the LHC.
I will now go to Alice. What are your expectations from Run 3?
We have made a fantastic progress in reshaping our detector into a very new device. So the time is extremely exciting for us. With the new device came also a new physics program focused on very heavy quarks plowing through what we call quark-gluon plasma, a state of matter that we think existed very early after Big Bang, and we're trying to understand how it works, what the microscopic structure of that matter is.
Thank you, Matthias. And Niels, today you just announced that the LHCb collaboration has discovered 3 new exotic quarks before the start of Run 3.
Amazing. We continue to discover new things every day, and indeed today we have this new state of matter with not 2 or 3 quarks, but 4 and 5 quarks. So that's something which we are still trying to understand, how these quarks bind together, and it's similar to what happened in the 60s when we first started this whole venue.
Of particle physics,
of particle physics. Yeah. And now for us particularly, this restart of the LHC will allow us to collect much more data. We replaced our total system, all detectors are new. We read out much more data, so with 10 times more data we think we can, even the most rare processes, we can study much better in the next coming years.
You call these quarks exotic. Are they different from the quarks that make us all and make this table and make all the matter that we know?
No, these are the same quarks, but composed differently. And it was kind of unexpected that we would also see 4 and 5 quarks binding together. And we still don't really know how this actually works. And we want to understand how our ordinary matter is actually binding together. Yeah. So it's very exciting.
Jamie, what's the challenge for the smaller LHC experiments that you showed us before?
Yeah, so as I said, there's 5 smaller experiments at the LHC. And I think what's particularly exciting is 2 of them are completely new, so they didn't exist for the last runs of the LHC. This is the Phaser and Snd Lhc experiments. And what's very exciting for those is they will study neutrinos, which we know exist. So that means they should really see these neutrinos for the first time produced by a collider in an energy that's never been studied, which is really cool. But also they will search for new particles which we don't know if they exist. They're sort of postulated from theories related to dark matter. So there's kind of 2 programs for these experiments related to neutrinos, which we should be able to make real measurements in. And then the search program looking for new stuff that might be there and would be really exciting if we find it.
Fabio, I would like to ask you, what's the plan after Run 3? Hopefully it's successful. Hopefully you clarify a lot of the new physics hints that have already appeared in Run 2. But then what's next?
Next comes high luminosity LHC. So we are preparing the upgrade of the collider and of the experiments to run at higher intensity of the beams, and so to produce more collisions. And this will open a new era of exploration in that we will be able to record at the end of the high luminosity LHC period, sometimes in 2040, 10 times more data than at the end of the LHC. And this, just to give you an idea, will give us something like 180 million Higgs boson produced then can be studied, a fraction of them can be studied by the experiment. And so, as was said before by Manuela, the Higgs boson is a fantastic discovery tool. And therefore, having a large sample of Higgs boson is absolutely important to make progress in our understanding of the law of nature.
Thank you very much. I would ask the social media now to send us more questions in, while we can now see again the experiments control room. Maybe Chris Parks, you want to give a comment on today's announcement? Let's see if we can connect with Chris at the LHCb. No, we come back, Chris. We are getting now a question from Natalie. When will we get the first round of data? Who wants to answer? I guess data are already coming in.
Data is coming in right now. They're filling up our computers. We look at the data as it comes in. And we also, just 1 or 2 days later, have another very careful look at it again. And then afterwards, it gets available and distributed around the world for people to search through it.
Because it's very important, Cern is a champion and a pioneer in open data policy. Maybe Fabiola can tell us something more about this.
Absolutely, Cern really promotes and embraces open data and openness everywhere in science. From we publish our articles in open access journals. We develop open software, open hardware, and we have a new open data policy that allows everyone to access the LHC data. So it's very, very important that the science we do and what we produce is available to everybody, to society, free of charge. And this dates back to the time of our founding convention, when this idea of open science was really already coded there, and was also demonstrated when Cern made the World Wide Web available for everyone to use and develop free of charge.
Yes, thank you for mentioning the World Wide Web. I wanted to ask Giovanni to make a comment on that. It's not only scientific data that is made available publicly, but we also foster the applications of the new knowledge that is produced here and of the new technologies.
Yes, absolutely. So I think it's important to mention that this openness of the laboratory is also reflected in our knowledge transfer policies and technology transfer. So our laboratory is using, as Fabiola mentioned, a lot of open source licensing. And what is really important for us is to make sure that our technologies are used by others. So what really matters for the laboratory is to make sure that those results are made available to others. And very often this happens via industry in the member states. So we need collaborators to make our technologies used in other fields. But our policy in general is very, very much open compared to many other national institutes I know of, at least.
Thank you. Mateo, you wanted to say something, I have the impression.
Yes, while we're here celebrating the top energy in proton-proton collisions, LHC is also a special device for colliding heavier nuclei.
Particles.
And we are looking forward to lead-lead collisions later in the year.
Yeah, maybe Mike, you can say a word about the program of the LHC. So you're able to collide not just protons, but different nuclei.
Yes, yeah. So for about a month of the year, we switch mode and we go to heavy ions. So we've traditionally done lead, but we've also done proton-lead. We've done xenon. So oxygen. So we have actually quite a bit of fun with this sort of as a tail end of the year. So the intensities of the ion beams are a lot lower than those of the protons. So we can relax a little bit. But some very interesting physics. So just to say that all 4 experiments are taking data while we're doing these ion runs.
Absolutely.
Yeah, you mentioned oxygen. I think it's in the plans also for run 3 to do a run of oxygen again. And, what is it for?
Let's ask the expert.
Yes. What are you doing, CMS, with oxygen collisions or at Alice?
I think it's for me to answer. While there are physicists in CMS and Atlas and LHCb interested in nuclear collisions, for us it allows us to study essentially the collisions which we understand in lead and the phenomena that appear there in a slightly different system. Scientifically, it's very interesting to understand the systematics of your observations. And LHC allows us to study different systems in order to exactly explore systematically the physics we're interested in.
Maybe I can just say something regarding the small experiments for
Yes,
the
please.
oxygen run, because actually one of the motivations is for the Lhcf experiment, which looks at the very forward direction of the collisions. And they're very interested in proton-oxygen collisions, because when you have a cosmic ray hitting the atmosphere, you get a high-energy particle that hits oxygen and makes a cosmic ray shower. And that's exactly what you can study in proton-oxygen collisions at the LHC. So this is a very nice sort of way that science can work together with a big facility like the LHC, really helping with cosmic ray physics experiments and providing data that's extremely useful for these.
Okay, we can go to the 4 experiments control room. Are we expecting any information regarding dark matter? Maybe we can ask this to the Atlas control room, to the Atlas spokesperson. Andreas Hacker?
Yeah, with pleasure. So dark matter is, of course, one of the very important signatures you want to look at. And the improvement of the trigger, so the online event filtering system we have implemented during LS2, so during the shutdown we just passed, will help us to look for dark matter. Dark matter is something which is, of course, in principle, if it is particles, we don't know whether it's particles, but most physicists believe it's particles, would be invisible. So it would be produced in the proton collisions, but then would be invisibly flowing through the detector. And so the trick we have is we produce the dark matter particles with other particles which are visible in addition. And so this means that through momentum conservation, we have one part with visible particles and the other part with missing energy. And this is the way we look for dark matter. And this is really one of the very, very important search analysis we do. And in particular, we think that since dark matter is massive, it might couple to the Higgs boson. So as was said before, we look also for the Higgs boson decaying invisibly into dark matter. These are very important analyses we are pursuing during run 3.
That would be a winning pair, I would say. Is CMS looking for the same thing, Luca?
Yeah, Paola. I hope you can hear me, yes.
Yes, we can hear you loud and clear.
Okay, thank you. Andreas already basically described we are looking for similar things, and I want to actually even emphasize more that we have prepared our detector in these 3 years, even to look more for this at the trigger level, but also for other kind of manifestation of new physics that might be linked to dark matter or manifestation of dark matter, but go even in other phase space, like long-lived particle that decay very late. And we have equipped our trigger and our detector with this capability much more than we are having before. So we are really ready to go much further than what we have done in run 1 and run 2. With this run 3 that we are still collecting data and we are actually enjoying seeing beautiful events here.
It's a feast of particles today. And we were talking before with Chris Parks, with LHCb spokesperson, about the hints for new physics that might be elucidated during run 3.
Yes, absolutely. We've got this brand new detector really for run 3, which is going to give us new capabilities. For example, we've got a new trigger system here. The trigger system is the thing which collects the events and decides which ones you can store for analysis later. And in our new detector, we're reading out the whole detector every time the beams collide, reading that information into a big software farm and making decisions on which events we're going to keep with a lot more intelligence than we could make before. And that's going to help to broaden our physics program. And yes, indeed, maybe it will allow us to make new discoveries.
And Alice, we're now getting back to you, Luciano Musa. What new discoveries would be your preferred for this new run?
Okay, so our scientific focus is the study of the quark-gluon plasma, which is created in the collision of lead nuclei. And this is the hottest and the densest fluids created in the laboratory, so where quarks and gluons are not confined inside the hadrons. And in run 1 and 2, we really made a lot of progress in understanding the properties of the quark-gluon plasma. But in run 3, we really shifted the focus towards high precision measurements, which on one hand will allow us to determine with unprecedented precision the macroscopic properties of the quark gluon plasma, as for instance its temperature, energy density, lifetime, viscosity, and etc. And on the other hand, we will try to understand how they are, these macroscopic properties are connected to the dynamics of the constituents of the quark gluon plasma in a microscopic picture. So we are really starting today a new exciting journey with a fully revamped detector, and we're really confident that we will be able to go very far, and looking forward to exciting new results.
Thank you very much, Luciano, and thank you very much, Alice. So Fabiola, it's a really exciting moment for physics right now. After the Higgs discovery, we said yesterday, it's the beginning of a new chapter. Even after 10 years, the Higgs is still a young particle, a young chapter. How do you feel that this run 3 is going to contribute to continuing the adventure with the Higgs boson?
It's going to be a very important step forward because, as was mentioned before, the Higgs boson is really a discovery tool. It's a very special particle with very special properties, which brings new interactions, and in some sense is related to many open questions related to, for instance, to the evolution of the universe, even to its fate. It's a key also to understand how the elementary particles are organized in families, and it brings also questions about the value and the lightness of its mass. So clearly it's related to some of the most important questions in fundamental physics today. Question where we are clearly missing something important, and I think that therefore that the detailed studies of the Higgs boson is absolutely of paramount importance. Yesterday, a very distinguished theorist, Nima Arkani-Ahmed, said you have to study it to death, and this is absolutely true.
Thank you very much, Fabiola. I'm just seeing if there are more questions. Yes, how does Cern collaborate with industry? This is for you,
yes,
Giovanni.
So yeah, industry is a crucial partner for multiple aspects. First, we buy things from industry, so we buy our equipment, etc. And this, I think, is a virtuous circle what we have built with industry, because what we ask them to deliver to us is always more complicated than what they did before. We are a kind of demanding client, but so we kind of push them to innovate, and then they can reuse those results in other places. So in this respect, industry is a crucial partner for us, and also for technology transfer, we need industry. So our technologies, I mentioned before, we want them to be used by others. We want them to deliver impact to society, but there is no single case of technology transfer which really had an impact, which didn't have an industrial partner. So industry is also the vehicle for our technologies that we develop here at Cern to reach society. It happens through industry. So we also collaborate with industry in the other direction, not to buy, but to pass them on our technologies, our knowledge, so that they can embed them in their products and services.
Thank you very much. Any more questions from social media? Yes, Farouk Serkini, will we see an expansion of the collider beyond 27 kilometers? Who wants to take this?
Yeah, ever ambitious. We've started a feasibility study for a 91-kilometer collider in the local area. So with the present complex acting as an injector to that machine. So this is about 2 years into a 5-year feasibility study. The machine is called the FCC. So this, in the first phase of its operation, we'd see this working with electrons and positrons as an electron-positron collider, before, after a decade or two, moving to protons. So a very ambitious project, very much at the early stages, and a little way from approval at the moment, but a lot of work going on there.
Thank you, Mike. So from Sarah, how much radiation is this producing and how it's being contained? Again, for accelerator physicists.
It's a good question, and something we take very, very seriously. We have a dedicated radiation protection group at Cern who monitor, control, and really carefully police the radiation aspects of what we do. If you go into the LHC in general, you can walk around the ring where the main dipole magnets are, and it's relatively low radiation. But when you get near the experiments, the actual collisions produce a lot of high energy particles, which create some significant amount of radiation in places. So the access to those areas are very carefully controlled and monitored. Everyone is carrying dosimeters. Access to the machines is very carefully controlled. You have iris scans going into the LHC itself, and something we take very seriously indeed.
Thank you, Mike. Some more questions. This is written very small. What did you do during the period of maintenance? Patricia, what did CMS do before starting Run 3 for the last 2.5 years?
Well, CMS did some maintenance, and we did some upgrades of the detectors. We did a lot of work on, we heard about the trigger systems, so we did a lot of work on the electronics and to try to get ready for the next run and make sure everything was in perfect working order to start Run 3.
At the same time, you continued publishing.
Of course.
The research didn't stop.
No,
because
of course.
the upgrades.
Many people were working on publications. We publish more than 100 articles in scientific journals every year. And this is something that is continuing to go on the data that we've collected already.
That never stops, right? For any of the four experiments. As we've seen, we got a media update from LHCb based on Run 2, right? Run 2 data.
Yes. I mean, we have terabytes of data, which is millions of gigabytes that need to be analyzed, and we use every day to do that, even when the accelerator is not running. For us, the last 3 years, as I said, we replaced all the systems that detect the smallest particles with the new technology to cover large areas with affordable technology to read out, nevertheless, all the data in an even faster way. So we really use this period to develop the new technologies for the next step.
Yeah, Manuela, how many theses were done at Atlas during the shutdown based on all data?
Well, you can imagine, CMS probably has very similar numbers. At any given time, we have about 1,200 PhD students. And on top of that, we have master's students and undergraduate students and summer students. And all these PhD students need to write a thesis, and they usually do it in about 3 or 4 years. So we have several hundred PhD students every year who are submitting their thesis and graduating around the world.
So you're not missing a quantity of data. Maybe we can go back to the we're going to go back later to the computing center. In the meantime, there is a question from Jamie. What is the goal and significance of phaser? And congratulations, LHC. So thank you for the congratulations. What's the purpose of phaser?
This is the best question we've got so far. So I'm actually the spokesperson of the phaser experiment, so I'm very excited. So phaser is really a neat idea, which is to place a very small experiment, but in a very special location. And the location is really on the beam collision axis line of sight, we call it. So if you collide your protons and you follow the line of the collision, after quite a long way, 300 meters or so, the LHC starts to bend away to make a circle, and you carry on, you go through 100 meters of rock, and you bump into an unused tunnel, and that's where phaser is situated. And by being situated in this very special location, it means that if you produce light new particles in the collisions, they're most likely to go along this line of sight and could be detected by phaser. So the purpose is twofold. It's to look for neutrinos, as I said, study neutrinos that are produced in these collisions, which are produced in the decay of light particles, but also to search for new weakly interacting light particles, like things like dark photons, which are postulated to theories which relate to dark matter and could be seen by phaser in regions which couldn't be seen by other experiments. So for me, it's really an exciting experiment, and we're really looking forward to the first data, which is coming right now.
That's fabulous. I was saying we could go back to the data center, but no, we're still getting more questions. That's great. So Birkin Netzdet is curious how much hard disk memory is needed for a data so big to generate this kind of experiments. This is a question for Enrica Porcari, the IT department leader, who hopefully is following us. Can we have the data center for the answer to this question?
Yes, thank you, Paula. Thanks for the question. So we currently have 10,000 disks for this, but as I said earlier, we don't only have disks. Disks come with good performance, but also a high cost. And so at the data center, we have to balance costs with performance needs. So as we said, a lot of our data is also for long-term storage. We use tapes for that need. And as I said, also we send the data through the WLCG. So we use different tools depending on what the need for accessing, as we heard from our colleagues from the experiments and from our partners worldwide. So we calibrate our offerings depending on the needs. But as I said, we expect 1.5 exabyte of data in this run. So there is a lot of disks, there is a lot of tapes, and there is a lot of networking capacity needed to share the data with our partners.
I can see some experts with you. Maybe you want to introduce them?
Yes, please.
Tim Smith. Fabiola described a lot about the open science and open data, so I'm responsible for a lot of those services.
Thank you, Tim.
Hello, I'm Maria Arzuaga, and I'm the service manager of EOS, our disk storage system for Atlas, EMS, LHCb. And we are very excited about this because we were preparing this with all the experiments, and we are ready. So with 600 petabytes and more than 1,000 storage nodes waiting for this data.
Thank you very much, our colleagues from the data center. Maybe there are more questions? Yes. So will there be any neutrino detections again for you, Jamie?
Yeah, so again, as I said before, there's two new experiments, two of the smaller experiments at the LHC just starting up for this run. So the phaser experiment and Snd at LHC. And both of these are designed to study neutrinos that will be produced in the LHC collisions. And this is the first time that a neutrino that's produced in a collider will be directly detected by an experiment. So this is really exciting. And one of the cool things is that the neutrinos that you get in this location where phaser and Snd are situated are extremely high energy. So they're generally like 1,000 times higher energy than most of the neutrino experiments which exist in the world. So they'll be able to really study these high energy neutrinos in a way which hasn't been done before. And that will, I think, really interesting for such small and quite cheap experiments. This will bring quite a lot to the LHC program in Run 3.
What's the advantage of studying neutrinos made in the lab compared to neutrinos that are flooding us right now, that are a deluge of neutrinos? We are immersed in a bath of neutrinos. Why do you want to make them in the lab when we have such an abundance in nature?
Yeah, well, of course, if you make them in the lab, then you know more about the sort of initial conditions. So we know what we're colliding, and we can predict how many neutrinos these will make and what energy they should have. And so then we can study those, and it gives you a sort of more well-defined experiment than we don't know what's happening in space inside the sun, etc. And so we do know at some level, but it's not such a well-defined experiment.
Complementarity is very important. Maybe Fabio can tell us a word about how complementary is this field with astronomy, astrophysics, and cosmology?
They are not only complementary, but they're also very close friends and very cousin. We are cousins essentially. We address, at least with astrophysics and astroparticle physics, the same questions. But we look at them from different perspectives. And so what we learn at Cern is very important as input also to astrophysics and cosmology. What they learn is also very important for us. So I think that the question that we are addressing, like dark matter, for instance, and others, are so important and so challenging to address, and also so intertwined, then deployment of several approaches, those from particle physics, accelerator-based particle physics, astrophysics, are absolutely necessary if you want to give an answer to those questions.
Thank you very much. We can get some more questions if there are any. Yes. What is the absolute best case scenario you're hoping to come from all of this? Again, for you, Fabiola, because you can answer for everybody. Otherwise, we should do it through the tablet, and it would take a bit long.
Well, I would say, of course, the dream is to be able to answer some of the open questions, and the best scenario, of course, will be to discover
new particles that can, for instance, tell us what is the composition of dark matter. That, of course, will be a dream scenario. Why dream scenario? Because today we know 5% of the universe, and we know that 25% is made of dark matter. So if we discover dark matter, then we increase our knowledge from 5 to 30%. It's absolutely extraordinary. But I think that our approach should be the right approach of research is to make progress step by step through measurements of what we know, through looking for new things, and I'm sure that the run 3 of the LHC will allow us to make significant step forward in our knowledge of fundamental physics and the universe. And for me, a discovery is also understanding how a very special particle like the Higgs boson behaves, or understanding how the quark-Coulomb plasma behaves. This is a big discovery.
Yes, we are at the frontier of knowledge, on the brink of new knowledge. Every step we make is a new step into the unknown. Mateusz, you wanted to add something on behalf of Alice?
Well, maybe not only Alice. Let's say a personal goal for an achievement. All of this will at some point end up in textbooks of physics. So we will pass to future generations the knowledge that they can further on build on that and go beyond where no one has gone before, or something like this.
Yeah. Yes. Yes, exactly. Standard model is already taught, maybe at university, I guess, not to undergraduates. So it's now 5:40, and we can take a last question from Pradeep Panikkar. If Higgs boson provides mass to all particles, then does it also do for the dark particles, the dark matter particles? I would give the chance to both Atlas and CMS to answer this question. So Manuela, what do you think?
Well, if it has mass, then certainly it has to interact, I think, with the Higgs boson. We don't know what this dark matter is, actually, right, Patricia?
Right, exactly. So, but we think it has, that the Higgs will interact with it. That's something that we're going to be looking for during run 3.
And on this question that takes us to the frontier of knowledge, I think we can thank everybody, especially our guests here, the protagonists of today. Feet, we can invite you to go and celebrate. You all deserve that. Thanks to the LHC control and also the other machine controls that have been flooded today by people, technicians. Thanks to the technical team. The live has gone fabulous, well, much better than in our wildest dreams. I hope the same is true for the LHC Run 3. Thank you, everyone, and see you next time. We have something as big to communicate to the world. Thank you.